We need to do some more terminology for graphs before we prove anything interesting. So a graph, G, is usually written down like this, V, comma, E. This is a capital V and a capital E. And this capital V denotes the collection of vertices in the graph, and capital E denotes the collection of edges in the graph. Okay, so let me write down an example graph. I'll call this vertex 1, vertex 2, vertex 3, and so on and so forth. And then we'll throw in a few edges. Okay, so we say that two vertices U and V are adjacent if there exists an edge between U and V. So for example, V1 and V4, they're adjacent vertices. V2 and V3, they're adjacent. Is V2 adjacent to V6? No, there's no edge between V2 and V6. Is V1 adjacent to V2? No, there are no edges between V1 and V2. Let's look at the edge V1, V4. We say that this edge is incident to V1 and V4. So this edge right here is incident to both V1 and V4 because it connects vertex V1 and V4. It has V1 and V4 as its endpoints. Remember, we write edges as these tuples where you list the endpoints that the edge connects. That's how you represent an edge. The degree of a vertex, so write degree. The degree of a vertex is the number of edges that are incident to it. So for example, the degree of vertex V2 is 1, 2, because there are two edges that are incident to V2. The degree of V1 is 1, because there's one edge incident to V1. If we drew a new vertex in this graph that was isolated, call it x, and it's not connected to any other vertex, then the degree of x is 0. And we have another notion called the neighborhood. So the neighborhood of a vertex is all of the vertices that it's connected to. So the neighborhood of, let's say, V5 is V2 and V6. I use these curly braces here. This is actually set notation, but we don't need to know any set theory to do graph theory. But the neighborhood of V5 is V2 and V6. The neighborhood of V3, well, that's just V2. And let's see, usually we abbreviate neighborhood with just N. So the neighborhood of V4 is just V1. I think you get the hang of it. And the neighborhood of X, it's empty because there are no neighbors for X. So this brings us to the first fact of graph theory. Your book calls it a theorem, but I really think of it as a fact. And that's called the handshaking theorem. So let's assume you have a graph G with M edges. then the following is true. 2 times the number of edges is always equal to the sum over all the vertices in the collection of vertices, the sum over all vertices of the degree of that vertex. Okay. So this notation here means take the sum over every vertex in the graph. This is read V in V. Again, this is just a little bit of set notation that we need to know in order to do this. So for example, here's a graph. It has vertices V1, V2, V3, and V4. You can see it has 3 edges. Now, let's take the sum over all the degrees of all the vertices in the graph. The degree of V1, what is it? It's 1. The degree of V2, it's 1, 2. The degree of V3, again, it's 2. And the degree of V4, it's 1. You'll see it's 1 plus 2 is 3, plus 2 is 5, plus 1 is 6. And this does equal 2 times the number of edges in the graph. Why is this handshaking theorem always true? Well, it's simply because each edge connects exactly 2 vertices. And remember, the degree of each vertex is the number of edges coming out of it. So every edge is going to be counted twice when you sum up over all the degrees. This edge right here, it's going to figure into when we look at the degree of V1 and the degree of V2, because it connects both V1 and V2. So 2 times the number of edges is always going to equal the sum over all the vertices in the graph of the degree of that vertex. Now we can conclude another theorem. So let's let G be a graph, and let's let V odd be all vertices with odd degree. And the theorem states that V odd, the number of vertices with odd degree, is even. So these two lines here mean the size of V odd. So the number of vertices that have odd degree is even in any graph. Why is that the case? Well, from the handshaking theorem, we know that 2m is equal to the sum over all vertices in the graph of the degree of that vertex. So we can break this sum into 2 parts. It's the sum over all vertices that have even degree of V, plus the sum of all vertices that have odd degree. Okay. So this 2m is even. The degree of all the vertices in V even are even. That's the definition of V even. V even is the set of all vertices that have even degree. So you're summing up a bunch of even numbers in this term. And then here we're looking at this term. Well, these degrees could be odd. In fact, they're all odd, because the definition of V odd is all vertices with odd degree. So in this sum, you might see 3, 7, 9, 5, and so on and so forth. But what we want to know is how many terms are in this sum. Since we have an even plus a bunch of even numbers, we have an even equaling a bunch of even numbers summed together, we know that this whole sum must also be even, because otherwise this number would be odd. So the value of this sum is even. But each term in this sum is odd. Therefore, there must be an even number of terms in this sum. For example, if you had 1 plus 3 plus 5, well, you're going to get an odd number. But if you have 1 plus 3 plus 5 plus another odd, 7, well, you're going to get an even number. Again, so if you have 3 plus 9 plus 1, you're going to get an odd number. But if you add another odd to it, say 5, 12, 13, 18, you'll get an even number. So yes, each term in this sum is odd, but there must be an even number of terms to make this entire sum even. Again, because we have even equals evens plus even. That means that the number of terms in this sum must be even in order to make the overall value of this sum be even. So the number of vertices of odd degree in any graph has to be even.